Hey everyone, today we are going to discuss about the asymptotes of a rational function. Now, whenever we graph a rational functions, we will be encountering asymptotes. Now, an asymptote is a line that the graph of a function that gets closer to but does not touch. For example, in our graph here, this is the function f of x is equal to 1 over f plus 1 plus 1. Now, observe that this graph here progresses towards to the right on this side and goes also to the left on this side. Take note that it gets closer and closer to this particular line here, but it doesn't get close to. This line is y equals 1. This is the line. Now, observe that the graph f of x gets closer and closer to y equals 1, but it never reaches that point. It just becomes closer and closer. And also do the same thing to the left. At the same time, this graph progresses upwards towards this line and downwards toward the same line as well. But it doesn't touch that line. That line is x equals -1. So in order for us to graph a rational function, we have to understand first what an asymptote is, so that we would know which part of the graph gets closer and closer to but does not touch at all. That's the purpose of the asymptotes. Now, there are three kinds of asymptotes. The first one is the vertical asymptotes, the second is the horizontal asymptotes, and the third is the oblique asymptotes. So let's try to solve some asymptotes in our examples. In our example here, we have f of x is equal to 2 all over 4x plus 1. So let's identify first the vertical asymptotes. Now, to solve for the vertical asymptotes, equate the denominator to 0 and solve for x. So what we're going to do here to solve for the vertical asymptotes is we get the denominator. In our case here, our denominator is 4x plus 1. We get that and equate it to 0. So we have 4x plus 1 equals 0. Why 0? If it's 0, then the function will become a number divided by 0, which becomes undefined. So we know that there's no value if it's undefined. That's why it becomes an asymptote. It reaches that part, it approaches that part, but it never reaches that part. So let's solve for x here. We'll have 4x equals -1. Divide both sides by 4. Divide both sides by 4. We will have x equals -1/4. So our vertical asymptote is found at x equals -1/4. Now, to understand the horizontal asymptotes, we have to understand first the degree of the numerator and the denominator. The horizontal asymptote is determined by comparing the degree of the numerator and the denominator. Please remember that the degree corresponds to the highest exponent that a polynomial have. So in our case here, our numerator is 2, so the highest exponent is 0. And in this case here, in our denominator, we have 4x plus 1, so we have a variable x here. The highest exponent is 1. So we're going to name our numerator's degree as n and our denominator's degree as m. So n is the degree of the numerator and m is the degree of the denominator. Now there are rules here that we're going to compare. So let's have horizontal asymptote. Now, if n is less than m, then the graph of f has y equals 0 as a horizontal asymptote. If n is equal to m, the graph of f has a sub n over b sub m as the horizontal asymptote, where a sub n and b sub m are the leading coefficients of the numerator and the denominator, respectively. If n is greater than m, the graph of f has no horizontal asymptote. So we have to understand first what case are we going to get, since there are three cases. Since our n is 0 and our m is 1, then we can say here that n is less than m, since n is 0 and m is 1. So what we're going to have is we're going to get y equals 0 as our horizontal asymptote automatically. Since n is less than m, then automatically y equals 0 is a horizontal asymptote. Lastly, we have the oblique asymptotes. Now, the oblique asymptotes works only on some specific cases. Oblique asymptotes occurs when the numerator of f of x has a degree that is 1 higher than the degree of the denominator, or n is equal to m plus 1. If we have that, we divide the numerator by the denominator using synthetic division, and the oblique asymptote is the quotient with the remainder ignored and set it equal to y. So the oblique asymptotes only occurs when n is equal to m plus 1. Let's check if our example here follows the oblique asymptote. Since n is 0 and m is 1, so 0 is equal to 1 plus 1, 0 equals 2. Since this is not a true statement, then it means that there is no oblique asymptotes. So the asymptotes of our f of x here, f of x is equal to 2 over 4x plus 1, are just x equals 1, negative 1/4, and y equals 0. Okay, let's have another example. Let's have here f of x is equal to x squared plus 3x plus 5 all over x plus 1. So let's identify the vertical asymptote, horizontal asymptote, and oblique asymptote of this function. Let's start first with the vertical asymptote. So to get this, we just get the denominator, x plus 1, and make it equal to 0. Solving for x, we have x equals negative 1. So this is the vertical asymptote. Next, let's have the horizontal asymptotes. Now, in order for us to solve for the horizontal asymptotes, we have to get the degree of the numerator and the degree of the denominator. To get that, we just check the highest exponent. For the numerator, we have degree of 2. That's the highest exponent. For the denominator, the highest exponent is, there's nothing written here, so it's automatically 1. Therefore, n is equal to 2, and m is equal to 1. So what are we going to follow here? We're going to follow n is greater than m, since 2, which is n, is greater than 1, which is m. So, in our conditions, if n is greater than m, then the graph of f has no horizontal asymptote. So this means that the f of x has no horizontal asymptotes. Last, let's check if the graph has an oblique asymptote. It should follow the form n is equal to m plus 1. This pertains to the degree. If this is true, then there is an oblique asymptote. Since n is 2, replace n as 2. And m is 1, so replace m as 1. So 2 is equal to 1 plus 1. 1 plus 1 is 2. Therefore, 2 is equal to 2. This statement is true, so it means that there is an oblique asymptote for x squared plus 3x plus 5 all over x plus 1. So, how are we going to solve for that? Let's go right here. We're going to get the numerator and divide it with the denominator. So let's write the function here again. F of x is equal to x squared plus 3x plus 5 all over x plus 1. We're going to get this and divide using synthetic division. So the coefficient of x squared is 1, coefficient of x is 3, coefficient of 5 is of course 5. Then x plus 1, we're going to have here negative 1. Please review about synthetic division. So bring down 1. 1 times negative 1, that is negative 1. 3 plus negative 1, it's 2. 2 times negative 1, that's negative 2. 5 plus negative 2, that is 3. So we have 1, 2, and 3, which corresponds to x plus 2 plus 3 over x plus 1. Now, the oblique asymptote here is only this part. This one only. We're going to remove the remainder. Therefore, the oblique asymptote is y equals x plus 2. Now let us check if the asymptotes that we just solved corresponds to the graph, if it really approaches the graph or not. Now I have here this graph. This is f of x is equal to x squared plus 3x plus 5 all over x plus 1, our example earlier. Now, if we type the asymptotes, we should be able to see that the graph approaches that line, but it never reaches that. So our first one is the vertical asymptote, x equals negative 1. This is x equals negative 1. If, as we can see here, the graph approaches that line, it becomes closer and closer, but if we can observe here, it never reaches that part. That happens upward and downward as well. Right here, it gets closer and closer, but it never reaches that point. Now, we don't have any horizontal asymptotes, but we do have an oblique asymptote, which is y equals x plus 2. As we can see here, the graph also approaches that line, but it never really reaches that line. It goes diagonally upward to the right and diagonally downwards to the left. So that's the purpose of the asymptotes, to check if the graph, to check the behavior of the graph on where it approaches. That's the kind of behavior that the rational functions exhibit. It approaches a particular line, but it never reaches that line, which we call asymptotes. Now take note that there are horizontal asymptotes if n and m are equal, and what we just do there is we get the coefficient of the highest variable with the highest exponent, then divide it. Whatever the result, that's the horizontal asymptote. So I hope you learned a lot in this lesson, and please review for everything that we have discussed so far, and thank you guys for watching.